Hello everyone, welcome again. Today we'll be talking about the metals module of the Year 11 chemistry syllabus, and in particular we'll be talking about the periodic table today. So by that I mean we'll be talking about trends, what we're going to see when we look at the periodic table and what kind of trends we can notice about the elements in the periodic table as we look around. Okay? So here is Mendeleev, and he is sort of the father of the periodic table, so it's a fitting place to start our study of the periodic table. So the first thing we're going to look at is the atomic radius, okay? And the atomic radius is basically the distance between the center of the atom and the furthest most electron. So for instance, if I had the nucleus here, the center of the atom would be here, and then if there was one shell and then two shells, the radius would be from here to here, okay? So that's what we mean by to the furthest electron. If there was another shell, the radius would be bigger. So essentially you can think of it as the more shells an atom has, the bigger the radius will be. Okay? So as we go down the group, so remembering that our periodic table has groups going down and periods going horizontally. So as we look down each group, the atomic radius increases, right? Because as we go down the group, we add more and more shells, and so the radius has to get bigger, as I just mentioned. Okay? Now, interestingly, across a period, the radius actually decreases. Now, that's because there's increased protons in the nucleus, and that causes a greater attractive force to the valence shell. So if we look at this little diagram here, this is going across one period. We've got lithium, beryllium, boron, and as you can see, the circles represent the radiuses, or radii. So as we go across, the radii actually get smaller, because if we have the outermost shell like this, and then we put in, say, 3 protons, okay? And as we add protons, there's an attractive force between the electrons out here and the protons here. So what happens is they tend to come in closer, and so the radius decreases. Okay? And that's why the radius decreases as we get more and more, as we go across a period, because we have more protons but the same number of shells. Okay? And here's a graph of atomic radius versus atomic number, and you can see that it kind of spikes up and down depending on basically as we go across periods and then sort of jump down to the next row or down the next group. Okay? So the next one we're going to talk about is electronegativity. Now what this is, it's the tendency for atoms to attract electrons in a bonding pair. So when we study water, we'll study why water is a polar molecule and why other things aren't polar molecules, and it's to do with this electronegativity. So if we had, for instance, carbon dioxide, which looks like this, what you'll notice is that because oxygen is more electronegative than carbon, the electrons will tend to hover around here rather than be near the carbon. Okay? And that's all that means. The electrons will tend to go towards the atom that is more electronegative when it's in a bond. Okay? And from this diagram you can see if this is our periodic table, as we go across towards these to the non-metal group, towards the noble gases, you'll see that we have increasing electronegativity. So the most electronegative would be F, and the least electronegative would be all the way on the other side down to here, francium. Now if you think about that, group 1 metals always want to get rid of their extra electron, right? They always want to give it away because it's easy for them to then get stability, right? So then if you think about it, their ability to hold on to electrons in a bonding pair is very, very, very low. So their electronegativity must be very, very weak or very small. So that trend kind of follows what we can see when we talk about ionic bonding and things like that. So most electronegative, and all the way down here at francium, least electronegative. Okay? So electronegativity generally increases across the period, and generally decreases as you go down the group. Now, down groups, the metallic character of the element increases, so it decreases the electronegativity. So electronegativity is sort of related to its metallic quality, or how metallic it is. And as we go down, the ability for the atom to hold on to those electrons decreases, because there's more electrons repelling and they're further away. So it sort of looks more like a metal, and so the electronegativity decreases. So then from electronegativity, we'll move to valence and reactivity. So remembering that valency is basically how many electrons you need, or the charge of your ion after you've reacted with something. So for instance, sodium has valency of +1 because it gives away its electron in a reaction, and then you're left with a positively charged ion, and that's the valency, +1. So as we go down a group, obviously it's constant because each member of one group has the same number of valence electrons, so their chemical characteristics would be similar, but their valency must be the same. So that's something that we can see straight away. And the most reactive metals are in the bottom left-hand corner of the periodic table. Now, if we remember that periodic table diagram from before, right down the bottom, there's a very reactive metal called francium, and that's because you've got a really weakly bound electron, one weakly bound electron, with lots of electrons repelling it, as well as it being a very, very huge distance away from the nucleus. So it's really weakly bound, so it can be flicked away really easily, and that makes it very reactive. So yeah, again, due to the very weakly bound outer electron. And the most reactive nonmetals are in the top right-hand corner of the periodic table. So the very most top right-hand corner, so fluorine and those very electronegative chemicals, because they really want to attract electrons, because they're only short one electron, so they really want to grab an electron. And because there's not many electrons repelling that group of electrons, or that bonding pair of electrons, it makes it very reactive. It allows it to grab electrons very easily. And that's due to the high electronegativity. So it's related to its electronegativity. Okay. So we've looked at basically chemical trends as we go down the periodic table, or as we go around the periodic table. So we looked at valency and reactivity, electronegativity, and atomic radius. So in the next lesson, we'll be talking about more physical properties of chemicals as we move around the periodic table. But we'll move on to the question segment now, and hopefully you'll be able to see and explain all of these trends that we see in the periodic table. So question 1, which of the following is incorrect about electronegativity? So A, electronegativity is the measure of the electron attracting ability of an element. That's not correct. It doesn't really attract electrons. It attracts electrons in a bond, not just random electrons. So across a period, so this is correct, because it does attract electrons, so it's not correct for this question. So across a period, electronegativity increases as the metallic character decreases. Yes, that's true. We want less metallic objects to have electronegativity, stronger electronegativity, so this is not the right answer. Down a group, electronegativity decreases as the metallic character increases. Yes, again, as you go down the group, you get more metallic character, and so it's less electronegative. So D is the correct answer. So nonmetals have low electronegativity as they need electrons to complete their octet in the valence shell. So because they need that extra electron, they want to attract them as much as possible. So nonmetals will have higher electronegativities than metals. Okay, so moving on to question 2. So if we have some mysterious nonmetal X and it has the valency of -1, so what would be the chemical formula when this element is combined with magnesium? Okay, so what is the valency of magnesium? The valency of magnesium is 2+, so that should immediately tell you which one it is. So it's not this one because the valencies won't link up properly, and you can see there's no charge here, so that's not correct. This one would have 4+ here and -1 here, and still there's no charge, so that's not correct. this one would have 4 positive charges and 3 negative charges, but there's still no charge up here. So that's not correct. So it must be this one, because there's 2 positive charges from the magnesium, and you've got 2 negative charges from the chemical X, and so there's 0 net charge. Okay? And that's how we work it out. So moving on to question 3. Explain why the atomic radius decreases across the period. Okay, so explain. So this is to do with cause and effect. So what is the cause of the atomic radius being decreased across the period? So first thing is, across the period, the number of protons increases. So remembering that as we go along, the atomic number is increasing by 1, and so there's more and more protons. This increases the force of attraction between the nucleus and the outer shell electrons. So remembering that diagram that I had, if you have the shell here and then the nucleus here, if you keep building up protons, there's a bigger positive charge in the middle, so that shell will condense because it's attracted to that bigger positive charge. Okay? And this increased attraction causes the outer shell to move towards the nucleus, making its orbit smaller. And that reduces the atomic radius. Okay? Because the orbit has come in towards the nucleus, you get a smaller atomic radius. Okay? It seems counterintuitive, but it's true. So we'll keep moving and we'll move to question 4. So a student wishes to create the most explosive reaction out of a reaction between only 2 elements. So this is quite a violent student here. So where on the periodic table would they likely source these 2 elements, and why? So we're looking for the biggest possible reaction. So if you want a very massive reaction, you need things that are very different. Okay? So a reaction between 2 oxygen atoms is probably not going to be very impressive. So elements from the bottom left and top right are the 2 most reactive sets of chemicals. So if we had the periodic table, if we looked at the bottom left and the top right, then we would see that those are the 2 most reactive. So if you put them together, then you're likely to get a very big reaction. So the bottom left has weakly bound outer electrons because of the large number of shells, and the distance between that valence electron is very, very big. Chemicals in the top right have the highest electronegativity, making them very reactive because they want to grab all those electrons as much as possible. So a reaction between these 2 sets of chemicals would likely produce the biggest reaction. Okay, so if we pick the bottom-most left one and the top-most right one, excluding helium, then we get a really enormous reaction. Okay? So moving on to the last question, question 5. Explain why the electronegativity decreases as you go down a group. Okay, so as we go down the groups, why does the electronegativity decrease? And again, we're looking at the explain verb. So as you go down a group, there are more electron shells. So if we look at the first one, there'll be this many. Then the second one, there may be 2. And so on and so forth as you go down, right? So the electrons in the inner shell basically repel the electrons in the outer shells. So if you have 2 shells, the ones in the middle will obviously be repelling the ones on the outside. And of course, the increased distance of the electrons in the outer shell weakens the force of attraction between those electrons and the nucleus, as well as that repulsion, so you get sort of 2 effects. So the increased attractive force caused by the increased number of protons is basically offset by the fact that the electrons are now further away. And also, the inner electrons are repelling the outer electrons, so the attraction force is very, very much decreased. So, and this reduced attractive force means that bonding pairs of electrons are not strongly bound by these atoms. So if it was to bond with something else, then we have a problem in the sense that there's all these electrons repelling it, and we're so far away from the nucleus that the attractive force is very low. So they're not really strongly bonding or attracted to that element because it has so many shells. Okay, so that's the reason why electronegativity basically decreases as you go down a group. Because we have more electron shells, more repulsion, and bigger distances. so that electron bonding pairs won't be able to be attracted as strongly by those atoms. Okay? So this wraps up today's lesson on sort of the chemical trends in the periodic table. So we looked at the trends in atomic radius, valence and reactivity, and electronegativity. So hopefully you've learned something, and in the next lesson we'll be talking about physical properties and how they vary around the periodic table. So I look forward to seeing you at our next lesson.